Unit 3, Control of HVDC Converter System. So the entire unit deals how to control HVDC converters. So normally in rectified side we can control by using the firing angle alpha. In inverter side we can control by using gamma, that is extinction angle control. The major advantage of a HVDC link is rapid controllability of transmitted power through the control of firing angles of the converters. Normally, the controlling process is very difficult in HVAC system because there is no firing angle or delay angle alpha or extinction angle gamma in HVAC systems. But in case of HVDC systems, there is a firing angles and also gamma. In modern converter controls are not only fast but also very reliable. So that means the continuity of power supply is possible in modern converters, and they are used for protection against line and converter faults. So the what is the basic principles of DC link control? The control of power in a DC link can be achieved through the control of current or voltage. We can control current or voltage in DC link. From minimization of loss consideration, we need to maintain constant voltage in the link and adjust the current to meet the required power. Normally, we are using the parallel circuits. The we must maintain the voltage as a constant. The voltage must be a constant to maintain power quality. So we can adjust the current to meet the required power in any system. So this is a basic equivalent circuit of HVDC system. So this is 3 into root 2 by pi VR TR cos alpha. This is a rectifier station. This is inverter station. 3 into root 2 by pi VI TI cos gamma is a inverter station. In rectifier station, we can control the power by using firing angle or delay angle alpha. In inverter station, we can control the power by using gamma, that is extinction angle control. So this is a converter valves. RCR is a rectifier resistance. RDC is a HVDC link resistance. Minus RCI is a resistance of inverter. Normally the resistance of inverter in terms of in negative. Already we see that in derivation. So this is a rectifier DC voltage, inverter DC voltage, current flowing in DC circuit, that is a HVDC link. How much current is flow is nothing but ID. This is the exact equivalent circuit of HVDC link. So please observe this one. This is a sending end side, this is receiving end side, this is sending end power transformer, receiving end power transformer. So this is a rectifier. EVR is a rectifier voltage, EVI is the inverter voltage. So the turns ratio is a NPR is NSR, primary side number of turns, secondary side number of turns. Normally in sending end side, we using step up transformers. In the nearer to the load center, we using step down transformers. The voltage sources EDR and EDI are defined by EDR is equal to 3 root 2 by pi NV EVR cos alpha R by using equivalent circuit. EDI, that is nothing but inverter voltage, is equal to 3 root 2 by pi NB EVI cos gamma I, where EVR and EVI are the line-to-line voltages in the valve side winding of the rectifier and inverter transformer respectively. From the above figure, these voltages can be obtained by EVR is equal to NSR into ER by NPR into TR. EVI is equal to NSI EI by NPI into TI, where ER and EI are the AC line to line voltages of the converter buses on the rectifier and inverter side. So ER and EI are the AC line to line voltages. TR and TI are the off nominal tap ratios. Tap changing using the tap changing transformers. So TR and TI are the off nominal tap ratios on the rectifier and inverter side. Combining equation 1, 2 and 3, EDR is equal to AR ER by TR cos alpha R. EDI is equal to AI EI by TI cos gamma I, where AR and AI are the constant elements. The steady state current ID in the DC link is obtained as ID is equal to ED minus EDR minus EDI by RCR plus RD minus RCI. This is from equivalent circuit of HVDC link. The DC current ID is equal to the difference between the rectified side voltage to inverter side voltage by rectifier resistance, inverter resistance and HVDC link resistance. Substitute equation 4 and 5 in above equation. We get ID is equal to AR ER by TR cos alpha R minus AI EI by TI cos gamma I by RCR plus RD minus RCI. The control variables in above equations are TR, TI and alpha R beta I. However, for maintaining safe communication margin, it is convenient to consider gamma I as control variable instead of beta I. Normally, the control is possible by using gamma and beta in inverter side. The power reversal in the DC link can takes place by the reversal of DC voltage. How to reverse the power reversal? Whenever we reverse the power from normally power flowing from rectifier to inverter, so the reverse flow from inverter to rectifier also power flow is possible. This is done by increasing the delay angle at the station initially operating as a rectifier while reducing the delay angle at the station initially operating as the inverter. Thus, it is necessary to provide both CEA and CC controllers at both terminals. What is the CEA? CEA is a constant extinction angle control. CC is a constant current control. Once again, CEA is a constant extinction angle control. CC is constant current control. The both control is need for both ends in the rectifier end and also inverter end. The feedback control of power in a DC link is not desirable because at low DC voltages the current required is excessive to maintain the required level of power. This can be counterproductive because of the excessive requirement of the reactive power, which depresses voltage further. The constant power characteristics contribute to negative damping and degrades dynamic stability. So, in overall, how to control HVDC? by using two controllers, that is a constant current controller and also a constant extinction angle controller.